All right, so so now let's take it and do the sequential composition, but let's try to do it with some of the ideas from randomized motion planning. Okay, so what I'd like to do eventually is give me a controller that works for every initial condition. That's sort of maybe my goal as a feedback designer, right? So if I design my initial time invariant LQR, I've got an initial set of initial conditions that work. Okay, let's say I just pick another initial condition at random somewhere in state space. Yeah, and let's say if it's already lands inside the funnel, I'll throw it away because I figure that one's already covered. But if it's outside, I'll do trajectory optimization, which this is wrapped around because it lives on the it lives on the torus, so it's wrapping around. That's a single trajectory that comes like this and goes back to the upright. Yeah, and I'll do trajectory optimization to get me back here, and then I'll stabilize it with time varying LQR, and then I'll compute that funnel here. Okay. And now let's just repeat the algorithm, okay? So I'll pick an initial condition at random. If it's inside the gray region, I'll just discard it. Those conditions are already covered. If it's outside that region, then I'll try to do trajectory optimization to get me back to somewhere on the initial tree. It doesn't have to go all the way back to the origin. It just has to connect back to one of the funnels, okay? And I'll stabilize that with time varying LQR and add it to the tree. Wash, rinse, and repeat, okay? And maybe you can try to fill the space with controllers. It might not be the minimal set of controllers you could get, but a simple randomized algorithm could take that recipe and turn it into something that does this sequential composition and really does fill the space, right? Yes?
So how do you decide which goal place within the gray area you're going to go to?
Awesome. So let me write down the sort of steps of the algorithm. So the initial version of this algorithm was called the lqrtree algorithm, for obvious reasons, although it doesn't really need to be LQR, right? So, so if you want to stabilize some point x0, u0, then I guess step one is to stabilize x0, u0 locally with time invariant LQR. Then we'll compute region of attraction. Okay, and then the next step is to pick a point at random. Call it X sample, just like we did before. If it's already in some region, we'll discard it and go back to this step. Otherwise, we'll do trajectory optimization. With a constraint that the initial time is my sample, and my final time is going to be somewhere on the tree. Okay? Let me write it a little differently. Okay, and so I'm going to answer your question more carefully here in a second here, and then we'll compute TVLQR feedback and cost to go. Then we'll compute the funnel. And then we repeat. You guys don't have to write that down. It'll be, it's available. Just think about it for a second, right? So, okay. So the question you're asking here is, how do you define where do you connect to? Which funnel do you try to connect to? And as an approximation, so you could try to land anywhere inside the gray regions. That's what we already talked about. Okay, but we're going to actually say, let's try to go back to one of the nominal trajectories, one of the trajectory optimization solutions you already had. So in the picture, it was one of the blue lines, not just anywhere in the funnel. We're going to go back to one of the blue lines, okay? And you can go back to anywhere on the blue lines, but since RRTs struggle in state space, we're using trajectory optimization here. We can do something a little bit more fancy to get back to the tree, okay? So the picture you should have in your head is that there's a bunch of trajectories moving around in state space. Okay, they all have funnels around them, but the tree really lives, is the trajectories, is the nominal trajectories. Okay. I'm going to do trajectory. I'm going to do somehow, I want to do something like an RRT to connect back to that trajectory, right? So I pick a random point. The way the RRT works is it picks the closest point on the tree, and it tries to go straight there, okay? And it does it by virtue of, it'll eventually work because it'll eventually pick a node that's close enough to the tree, epsilon close to the tree, so it'll connect successfully. I don't have that property here because I will never pick a node that is inside my funnel, right? I'll never pick a node that's inside here. So I have to somehow connect to the tree from farther away. And we have to do something fancier, I think, like trajectory optimization. Okay, so we're going to do trajectory optimization instead, which is way more expensive than doing the simple RRT extend. Yeah?
Maybe is one option that you could run the RRT backwards in time from your goal, and then when you do this process, you look to see which RRT nodes aren't in the funnel yet, and then connect them back to their parent.
That's a great idea. Yeah, I think that could work too. I think that this one has some nice properties in the sense that you end up with very, very sparse trees, and we can still guarantee coverage. Okay, so in the same weak probabilistic time as time goes to infinity way to get coverage. Okay, all right. So we're going to do trajectory optimization, where it starts doing trajectory optimization, and there's a cost, or there's a constraint which saying the distance between my final point on my trajectory and the tree is 0. Right? So you can imagine writing down the function, which is the distance from the tree here, like the level sets will look something like this. That's a computational object you can define, right? The distance from the tree, right? So we say that distance has to be 0, and it gets pulled towards the tree. So the answer is you don't have to pick a priori which funnel. You're going to let the trajectory optimization resolve that, and that allows it to be much more flexible. If I pick a point which is not reachable in some small amount of time, the trajectory optimization will just fail. But in practice, what you see when you do this is that the trajectory optimization tries to connect, and then as it gets feasible, it'll walk along the tree until it finds a feasible trajectory, snaps in, and off we go.
So what if the trajectory that you just computed, that you're connecting to the tree, has wider funnel than the one that you connected to? Then you can end up outside the trajectory that you're connecting to.
So we find the biggest funnel for which the end always lands inside the beginning of the next one. That's a constraint in the search for the funnel. So it'll always have that guarantee. We could be sacrificing stability for that, but we can make sure that happens. Yeah?
So when the length of the trajectory that you have to extend isn't so predictable, are you just fixing the number of steps that you have in your trajectory optimization and running with that?
So you can do clever things like dynamically sample, like if you notice it being stretched too far, then you just resample and continue your optimization. And that's something you can do in any trajectory optimization. And there, or if it's getting too narrow, you can stop and resample and do that. And those tricks do help. But it'll work and just be less efficient if you end up with nodes that are too far apart, and you can put a constraint on how, you put a constraint on how much you're willing to accept that to be stretched out. Yeah?
And your trajectory is represented by finite set of points because it disconnects, right? So
Yes.
how do you compute distance to the trajectory?
Good. So, well, the distance to the trajectory you can do, so it needs to be a function that's differentiable and smooth enough for the numerical solver to not choke on it. But in practice, I search for the closest point on, there are discrete points here, right? In practice, when I'm computing that, I'll just look at my current state, I'll look for the closest point, and then look at all of the neighbors, or all the branches coming in and out, and do a search along the local cubic polynomial to find the closest point. Yeah? Yeah?
How do you see your trajectory position?
Randomly, and that's important because you need to in order to have probabilistic completeness, you have to have you have to rely on the trajectory optimization eventually succeeding. So the weak way that we do that is we say that if we run a trajectory optimization from an initial point, it has to get to some other point. If a path exists, if I just try my trajectory optimization infinitely often with different random seeds, it'll eventually succeed. And that's a soft answer, but that's the nature of the probabilistic algorithms. You rely on things like that. Okay, so there's the property that we're all hinting at here now is it's a notion of probabilistic completeness, but in the feedback case, we call it probabilistic feedback coverage. Okay, the property is that instead of saying if I from some initial condition and a goal, I will eventually find a path if it exists. This is trying to say more. It says there is an initial set of initial conditions for which some path exists that will get me to the goal. Call that the reachable set, or the backwards reachable set. Okay? The claim here is that eventually, as I run this algorithm long enough, my funnels will cover will cover the entire reachable set. Every initial condition that could get to the goal will eventually get to the goal, given the feedback control, given this randomized algorithm, okay? And the argument goes roughly like this. So this is an example where the reachable set is, we defined a dynamical system which had a trivial known reachable set. It couldn't ever go across that red line, okay? And it was trying to stabilize this point here, so it gets a nice big region, okay? And then it gets more and more regions, okay? And eventually even though there's a straight line defining the reachable boundary, it'll eventually approximate that with arbitrary ellipses, right? So with some probability, if there's a region that's not in a funnel, it'll eventually be sampled with some probability. By randomly starting my trajectory optimization, it will eventually connect back to somewhere in the tree with some probability. And by virtue of having the system be locally valid, the linear system being locally valid, it will eventually have some measure zero. It'll take away some finite measure. It'll add a funnel of some non-zero volume to the tree. Under the proper assumptions, it will take that piece away from the tree, and it will eventually cover the entire space. Yeah? So in that sense, it's a dynamic programming type algorithm, but not saying it's optimal everywhere, but it's provably good enough everywhere.
When we're switching funnels, how do we make the transitions mild from our actuator perspective? Like, it may be a different controller altogether, and it might need suddenly a huge torque. How do we make those transitions smooth?
So you can add the constraint that you have on my nominal trajectory has to match where it connects. So you can come in and have a smooth connection to the existing tree, and then you can solve your LQR with the final constraint for my TV LQR being the TV LQR solution at this point. So you actually, it would be as if you did a TV LQR solution all the way along the entire system to the goal, so it'll be smooth. If a disturbance comes in and knocks you away into some other funnel, you could have a discontinuity, but you also had a disturbance that something, so. Okay, so this notion of probabilistic feedback coverage is a little bit richer, okay? But so right now, this is sort of the best solution I can, this is, if you ask me how would you try to solve an acrobat or a cart pull to completion or something like this is the best answer I know how to give, right? That I can guarantee that the system will eventually get to the goal, right? So this is, when I showed you this before, we didn't have the language of lqrtrees, but if you remember, the cart pull would swing up from all the different initial conditions, right? This was running an lqrtrees controller. If you notice, the title was simulation-based. Philip, the author on this, was keen on not using sums of squares for the verification. He wanted to have something that was data-driven so that he could potentially also use the hardware to do verification. So he's doing approximate funnels using the simulation, but he can, if the simulation is deterministic, he can give some of the same guarantees. Anyway, so that stabilizes from a large range of initial conditions, right? When we showed you the perching results before, I told you the time-varying LQR story, and I gave you this picture. But the reason the thing that it took to make it work from lots of different initial conditions for Joe to throw it and have it always land on the perch was actually that he was doing more than just one time-varying LQR controller. He had a whole library of time-varying LQR controller. I'm sorry that the X is flipped. So now, yeah, same thing, but just mirrored. This is sort of rendering of the lqrtrees to get to the end, yeah. And he didn't. Now that was a 7-dimensional state space, and then larger for when he included some extra terms in his actuator model. Okay, but at least 7 dimensions. And he didn't try to fill that whole space. Filling 7 dimensions is maybe a tall order, but he had some set of initial conditions that he cared about, which was roughly what came off the launcher or out of his hand. Some initial velocities he cared about, and he sampled from there and made sure that was covered, right? Some subset of the 7-dimensional space, and that was covered. Okay. Okay. Another point is that you can actually you can handle state and input constraints. The trajectory optimization could certainly handle it. The TVLQR won't handle it, but you can verify where those state and input constraints break your verification. The sums of squares can handle it. Okay, so if you have an airplane through a forest and you do trajectory optimization through the forest, okay, you can compute a trajectory and a funnel, a controller that just sort of ignored that, but you can then do some simple computation. Another thing that Ani's been doing nice work on to sort of efficiently crop those down to be funnels that are actually valid. This was a cartoon I made early on. The actual funnels will look a little different than that in the corners, but you can chop them, trim them down to handle state constraints and everything too. Okay, so if you run the LQR tree controller on this world, just if you ran an RRT backwards from the goal, like you're saying, then you would get trajectories that fill all those nooks and crannies and get you, right? So from every initial condition, you'd have some path. Here, if you run the LQR tree to completion on this, you'd get funnels that fill all the nooks and crannies and always give you a feedback controller that's guaranteed to get there, even with the inequality constraints and everything like that, right? The RRT will never cover the entire space, right? It's always measure 0. It's always just trajectories, right? This will actually cover every trajectory takes out a finite volume of space and will eventually cover the space, right? You can do all this stuff for the hybrid systems too, right? So we talked about how would you compute a time-varying stabilization using the transverse coordinates for the hybrid system. We talked quickly about it. But if you had a hybrid limit cycle and you build a coordinate system that goes along the limit cycle, lines up with the hybrid surfaces, you can get a time-varying Lyapunov function out. You can do sums of squares to estimate the regions of attraction to a time-varying limit cycle. So for the compass gate, the picture would be that you have a nominal limit cycle with a discontinuity, right? You can compute the regions of attraction to that limit cycle using the sums of squares, if you stabilize it with LQR, for instance. And you get this initial gray region that follows the trajectory. It's not defined across the jumps, of course, but it follows the trajectory everywhere else. And then you build a few controllers with trajectory optimization to cover the reachable space, right? So I don't know, but maybe this is a sort of a natural thing to think. Like I've got a nominal walking controller, and when I'm close to the limit cycle, I'm just doing my nominal controller, right? And then when I get a big bump, I turn on a different controller that gets me back, and I do my thing, okay? And the claim is that if you're willing to do feedback motion planning instead of just trajectory motion planning, then maybe you only need a handful of these reactive controllers to get you back to the nominal limit cycle and fill the space as well as you can. And then the hybrid story has another analog to the complementarity version of contact. That's something that Michael's been working on. So you can do the same sort of work sort of through contact where the verification happens with the complementarity constraints, right? And that's a deep and rich story. So it just happens that Ani and Michael are the guys that have been pushing these stories the most. So if you have any questions about them, you should come ask them, right? But there's a version of the story that works through contact too. It's numerically much harder than the other ones, so we've only solved smaller problems with it so far. But it could potentially fill a space with contact. Okay, and then the last idea, I know I'm almost out of time here, just to sort of put it all together, a very natural question then would be, okay, I've stabilized the goal. This is like putting all the tools together. I sort of know how to, with trajectory optimization, Lyapunov functions, RRTs, put all together. You give me a goal, I can stabilize it from all initial conditions with a lot of computation potentially. Okay, but what if I don't have a goal, but maybe I'm just moving through the world and obstacles are appearing in front of me? What if I have to do this online? I don't have the luxury of having a perfect model of the environment, right? And that's another thing that Ani's been pushing on really nicely, is this notion of using libraries of funnels to do online motion planning. And I'll just show you some of his quick success stories here. But you can build you can pre-compute libraries of funnels. So if you're an airplane, maybe you have a funnel for flying straight, you have a funnel for bank turning, a funnel for bank turning the other way, maybe some small library of funnels. And for each one of them, you compute what initial conditions and what post conditions, sort of some nice big region, and maybe you ask for actually convergence in that region for some technical reasons. Okay, but if I have sort of a library of motions that I could potentially execute, depending on what the world throws at me, right? Then if you compute them in the right way, that when there's constraints that appear in front of you, you can trim those funnels down, like the picture, the cartoon I gave you when the polygonal forest trims my funnels down. I can have, if I have a form of stability inside my funnels, then every sub-level set of my funnel is also a funnel. So I can trim it away and make smaller funnels that are going to work in the real system. And then you have a nice planning problem, which is I've got a library of funnels, I have a goal, and I've got some new obstacles. Find a way to compose those funnels at runtime in order to get to the goal, or at least to not crash in the receding horizon sense. And you can do that with uncertainty, unlike trajectories, which you can't really talk about robustness of a trajectory, right? Because an airplane having some nominal trajectory like this, if the wind's blowing, that's not a feasible trajectory for the original system. But a funnel can be robust, right? A funnel can actually, I can still say, even if the wind's blowing, or if I don't know what the wind's doing, I can stay inside this funnel as long as the wind is between 0 and 5 knots or something like this, right? So he builds these libraries of funnels and then does online planning, trying to find solutions that on the fly. He's actually planning a couple steps ahead, but just drawing the one that it picks online. Okay, and yeah, there's a big project that Ani's been pushing on to try to make an airplane fly through a forest at ridiculously high speeds. So he's got these airplanes like this, and he's making trajectory libraries for the real airplanes. We've got bigger versions that have cameras on board, and we're trying to do the Return of the Jedi Forest of Endor scene, basically. Very explicitly, actually. Yeah, so that I want to just tell you that story exists, but Ani's your man if you want to see some details. Okay, so I hope that feels like maybe, it's a new idea, but it's just all the stuff we already talked about put all together in one in one big story. Good. I will see you on Tuesday.